Hello, everyone. Good evening to all. I am Abhinav. I am currently working in Decibels Lab as a BMS algorithm development engineer. So primarily, I take care of cell testing and battery pack testing and model validation, such as cell modeling and battery pack modeling and validation. So apart from that, I have also worked on algorithm development such as SOC and SOH estimation using various approaches. I have also worked on equivalent circuit modeling and also have used Kalman filters as such for algorithm development. So in this webinar today, we will be exploring this concept of temperature estimation of lithium-ion cell. So basically, why is it important to go for temperature estimation? What is the significance? So what are the different approaches? And also just a quick overview of how the model will look like and some of the results that you can expect. So this is the content in the entire nutshell of today's program. So what all we'll be looking at. So first, we will start with understanding how lithium-ion cells behave with temperature. So how their capacity or how their resistance, how its health and condition continuously keeps on changing with respect to the temperature that it faces. And also we look into something what is called as influencing or aggravating factors, because basically these are factors that can either make the situation much more worse, or it can start to deteriorate the cell in a certain way. So we will look into that. Then we come to the need for lithium-ion cell temperature estimation. So why is it important to go for temperature estimation and how does it help? So then we go into the sources of heat. So basically, what are all the sources of heat? What causes the cells to heat up? We will look at that. So all that has to do with the internal part, the internal chemistry and such. So then once we're done with this, we go to the practical part where we try to see what are the different approaches. So there are numerous approaches, and among them we will be focusing on one most important one, uh, which is called as lumped parameter approach. Okay, so lumped parameter approach is basically one of the simplest models. So we will have an overview of this part, and we'll see how this can be modeled using simple mathematical equations. Okay, so once we are done with this, we will have an overview on the model components, what are all there, along with the inputs and outputs, and we'll have a overview of the simulation results as well. So this is the complete uh, like the overview of the contents for today's program. Okay, so first we'll start with the thermal behavior of lithium-ion cells. So we'll start with this, where we will see how exactly the discharge capacity of the cell behaves with respect to temperature. So you can see here the complete range of temperature over which this particular cell has been uh, subjected to. So starting from -20 to 45. So as and when the temperature goes on increasing, you will see that the performance goes on increasing, as in to say the performance goes on getting better. And as and when you decrease the temperature, the performance goes on getting worse, right? So at 45 degrees, it's able to output more than 100% of its capacity. And at -20, it's getting less than 50% of the total capacity as the output. Okay. So this is because what happens is that as and when the temperature goes on reducing, the internal chemistry, that is the main reactions that happen inside the cell, they become more and more sluggish, as in to say they are not able to sustain themselves. So of course, if you go on dropping the temperature, the available energy in order to complete these reactions will also go on dropping. So because of that, you notice that there is a significant drop in the voltage and also the available capacity. So if you notice this in one cell, so surely you will be noticing a chain reaction as such, even on the battery pack level, right? So just as how you see a change, a significant change or a significant effect on the capacity for one cell, you will also see it for the internal resistance. So this is how the resistance of the cell looks like, as in when the temperature goes on changing. So you can see at lower temperatures, the resistance is higher, and at higher temperatures, the resistance is lower. So here you can see that there are two types of resistances. One is ohmic and one is polarization. So just to have a brief introduction to this, ohmic resistance is because of the materials inside the cell. and polarization resistance is because of the chemical reactions inside the cell. So each of these are affected because of the temperatures inside. So once again, the same explanation comes here as well, is that the available energy goes on reducing as in when you go on dropping the temperature, right? So this is like one of the most significant effects of temperature, and it plays a very vital role in the performance of the lithium ion cell, right? So we have understood for capacity, we have understood this for temperature, for resistance. Now we can also look at how it affects the uh, performance in real life. So like especially when you're going for storage and when you're going for operation, that is when you're using it continuously, charging and discharging, how it will behave. So on the left side, you'll see something called as calendar aging. The calendar aging is basically like a slow deterioration or degradation due to storage, continuous storage. And the storage is usually like over a very long period of time. So basically like over like 60 weeks, 1 year, 2 years, things like that. So like you can see here, there are three graphs that correspond to each temperature. So 35 degrees, 50 degrees, and 65 degrees. So like the higher the temperature in terms of storage, the higher the faster the degradation, right? So the reason for this is because if you go on increasing the temperature, then interior like materials and all the chemicals will go on getting consumed continuously. So if they go on getting consumed continuously, naturally even your available capacity will drop, right? So that is why like certain manufacturers will provide a data sheet in which they will provide a certain temperature range in which you're supposed to store the cell. So not more than 35 or 40 degrees Celsius to prevent like less than 5% loss of capacity. Right. So this is during storage. So during operation, here you can see there are actually like a very wide range of effect that you can see here. So let's start with the high part where the temperatures are exceeding 45 or 50 degrees Celsius. So then what can happen? What are the results? Like basically you can see here complete loss of capacity, loss of power, loss of mechanical stability. So basically inside the components will no longer be able to sustain the load basically in terms of current or even in terms of physical load. So they will go on getting gradually getting deteriorated, right? So rise in internal resistance. So basically these are all like effects. Basically these are all something that are happen because of the various reasons that have been mentioned here. So things like electrolyte decomposition or side reactions or parasitic reactions. So basically these are unwanted reactions that happen inside the cell that can cause damage to the interior materials. So decrease of available lithium ions. So like lithium ions are continuously exchanged between anode and cathode during operation. So at high temperatures, what can happen is the material can get basically like so saturated that it will no longer allow the lithium ions to correctly get deposited on the in the material. So all these are contributing factors to such results like this, where you can go for capacity fading, power fading, energy loss, and rise in internal resistance. Eventually, all of this will lead to like faster and faster degradation, right? So now we come to the green area where like they say maximum cycle life. So basically this is the area or the most recommended temperature range within which the lithium ions are very stable. So here like such effects are like minimized, right? So at the bottom part, when you go into low, here especially like very, very low temperature, like 5 degrees or 0 or -10 like this, here what can happen is like the reactions as explained before, they won't have enough energy. So if they don't have enough energy, the ions don't get absorbed properly, and because of that a particular phenomenon called as lithium plating can occur. So in which basically like lithium ions get deposited on the surface of the electrodes, and they can cause like solid lithium plates to form, like lithium layers to form on the electrodes. So because of this, once again, we have a result like this, that is capacity or power fade, energy fade, rise in internal resistance, decomposition of the electrolyte, then like complete degradation of the anode and cathode material. All of this can happen, right? So this is the adverse effect of temperature on the lithium ion cell during operation, right? So apart from this, we also have the effect on cycle life, right? So here you can see just as a simple case where if you're taking a cell and say you subject it to 1C charging and 1C discharging, so at various different temperatures, so 25 degrees, 40 degrees, 60 degrees as such. So you can see how much difference there is in terms of operation. So 25 degrees is optimal. It gives you a good amount of cycle life, but still a decent amount of capacity available left. Then we look at 40 degrees, which is showing slightly lesser available capacity. And then at 60 degrees, where it is showing complete deterioration, right? So it doesn't even live up to the required number of cycles. Yeah. So this is the effect of temperature on lithium ion cells, right? So which is what we see in those all the graphs that we see that we have encountered there. So what are all the aggravating factors? So aggravating factor is something that can make an existing situation even more worse, right? For example, suppose the cell has experienced a temperature of 40 or 45 degrees. So what are all the factors that can make it even worse? So especially things like high charging, high rate of charging or high rate of discharging. So if you already have a temperature which is very high for the cell, so for example above 40 degrees, and if you continue to charge it very high at high rates or discharging it at very high rates, then it can cause the cell to approach what is called as thermal runaway, TR. I am abbreviating this as TR. So TR stands for thermal runaway. Basically, it's the temperature where the cell can spontaneously ignite and uh, it can catch fire and it can also explode. So there are many such cases where the cell has overheated, especially during charging, and it has led to thermal runaway. Yeah. So of course, apart from this, we also have ambient temperature, which is main contributing factor. So if the ambient temperature itself is already high, then it can lead to the cell not rejecting enough heat. So that can cause heat accumulation within the cell. So that is one situation. The other is age of the cell. So if you're comparing the heat dissipation of two cells, say for example, one cell is fresh condition and the other cell is not in the fresh condition. Suppose it is aged. So in that case, what can happen is the aged cell has already has having a large amount of internal resistance, and a lot of its material is already degraded inside. So because of that, it can not have enough ability to reject heat. So again, heat can get accumulated and start to cause further deterioration. So age of the cell is one factor. So other things are side reactions or parasitic reactions. So these may not be directly influencing factors. These are indirect influencing factors. So basically because these are primarily dependent on the main reactions themselves. So if your main reactions are somehow affected in some way, suppose they're hindered or they're obstructed in some way, then the side reactions can come into picture and they can kick in and take more effect into the thermal behavior of the cell and cause more and more heating. So this is one way. The other one is manufacturing defects. So if you are having a defective component inside, for example, incorrectly manufactured electrode or some impurities present within the electrolyte, so that can cause once again some hindrance in the heat rejection and can participate in the reactions, and once again it can lead to some complex scenarios. So these are all aggravating factors. So basically these are the ways in which the cell performance can go on getting degraded further and further. Yeah. So that brings us to the need for lithium-ion cell temperature estimation. So why we go for estimation? So first and foremost, it gives us a very clear idea of how temperature is distributed within a particular cell. And if we know how it is for one cell, then we can understand how it can go on for the entire battery pack, right? So it can also help in optimizing the cell and battery pack thermal management. So for example, if you know how one single cell is behaving in terms of thermal in some different temperature scenarios, then you can choose the right thermal management options, whether what type of cooling you can choose, whether you can go for passive cooling or you can go for active cooling. So, and based on this, you can go for cost effective solutions. So when to go for passive or when to go for active. And then you can go for minimizing the cell degradation. So you know exactly how to cool the cell, then if you know that, you can definitely minimize your cell degradation and reduce the effect of extreme temperatures on the cell behavior, right? So more towards the control algorithms is where you get to develop efficient thermal control, especially in the BMS, the battery management system. So if you know how your cell behaves in different temperatures, then you can have effective control algorithms. So especially in terms of over temperature and under temperature protection systems. So these are all the requirements that we can say that, or we can summarize, and then we can say that these are the ones that are required for temperature estimation. This is why temperature estimation is required, right? So now we come to the main part. So we will try to see what are the sources of heat in a lithium-ion cell, why exactly heat is generated, and what are the possible sources. So first, we will focus on the main reactions that occur within the cell. So anode and cathode are the two main participants within the cell, and they are the ones that are involved in the reactions, right? So there is something called as redox reaction. So redox reaction is basically, it's an abbreviation for reduction and oxidation. So reduction, and the second part is oxidation. So if you combine these two reactions, you have the main driving reactions of the cell. So when you combine these two, you have the redox reaction. And you can see, just as an example, if you consider what is called as a lithium cobalt cell or lithium cobalt oxide cell, so that is basically one of the most commonly used lithium ion cells. So if you consider the reactions, the oxidation and reduction reactions have been shown here. So basically, these reactions are exothermic in nature. So these reactions are exothermic in nature. So basically, that means they release a lot of heat. So these are the main reasons. This is the main reason as to why a cell generates a lot of heat. And if you classify these reactions, then you can consider them into two parts, or you can say two categories. So reversible heat generation and irreversible heat generation. So we'll try to understand each of them here. So reversible heat generation is basically because of the internal reactions. So the same reactions that we have mentioned here. So reduction reactions. Since these reactions are reversible, as in to say, during discharging, you have a certain set of reactions. During charging, the same reactions will occur, but in the opposite direction. So these reactions are reversible, as in to say the energy can be dissipated and gained back. So that is why reversible heat generation happens. And irreversible heat generation is because of the internal materials. So for example, we have the electrode material. So for example, we have electrode. So there are certain materials for the electrode itself. So like graphite, along with some binders, some adhesive materials, some cathode materials like lithium cobalt oxide, and copper, aluminum. These are all mixed into the electrode material, and this can cause some losses. So electrolyte, that is another loss. That is another way in which some losses can happen, right? So these are all some of the materials that are present inside. So of course, you also have the current collector. So there are other materials as well inside, like separators, binders, and things like these. So all of these contribute to what is called as irreversible heat generation. So basically heat or some energy that cannot be gained back, right? So this is also called as Joul's heating. So or also you can call this as ohmic loss. So all of these they mean the same thing. Basically, heat is dissipated in an irreversible manner. Okay, so these are the two sources of heat inside a lithium ion cell. So whether you consider whichever format of cell you consider, as a prismatic or a pouch or a cylindrical, they all generate heat in the same way. Okay, so so now we have understood the main sources of heat. So then if you further go on into the a mathematical format in which you can represent heat, So then you can like consider something called as entropy. So entropy is like the change in order, or you can say the change in energy of the entire system. Okay, so before we go into this, so an important thing that I have to mention here, it is called as Gibbs energy. So Gibbs energy is the total available energy within any given closed system. And for an electrochemical cell, since it is also a closed system, for an electrochemical cell, the Gibbs energy is represented like this. So since we are talking about total available energy, so we have to consider Gibbs energy as conversion of uh, chemical energy. So we have chemical energy in the cell converted to electrical energy. So this is idealistic, since since we like idealistically we prefer that all of the available chemical energy is converted to electrical energy, or reverse, as in electrical energy to chemical energy. This is your what is called as Gibbs ideal energy. So this is what is preferred, but realistically this is not the case. So here what actually happens is chemical energy, so this is converted to electrical energy plus heat. So heat energy, heat is what is developed every time you convert some amount of chemical energy to electrical energy, and some heat is released. Yeah. So this heat, as we have discussed earlier, it can be represented as reversible or irreversible heat. And this is the way in which you can represent a reversible heat. So basically, this is heat that can actually gain back, or some amount of energy that can be gained back into the system. Yeah. So this is represented by the product of change in entropy and temperature, right? So we will not be going like in depth into the derivation part. So that is not actually within the scope. We just have to like know what are the different available sources of heat. So this is reversible source of heat. There is also irreversible. So as I said, this is because of the Joule effect or ohmic losses. And this can be given in two ways. So either you can consider I squared R losses, so which is basically I squared R is the total internal resistance present within the cell, or you can take it as OCV, the ideal voltage minus the measured terminal voltage into the total current or the total charge passing through. So this can be like the total irreversible heat that is calculated. So if you take the total heat, so Q total, it will be Q reversible plus Q irreversible, right? So it's a sum of these two put together, right? So more in realistic conditions or in realistic scenarios, you will see that this is actually contributing lesser to the heat generation, and this portion is actually contributing more to the heat generation, right? So this part is more, you can say most, and this is lesser. So again, the reasons for this, we will not go into complete understanding of this. Just for the basic understanding of how you can represent the heat generation. That's how through reversible and irreversible heat generation. These are the equations, right? So now we have like understood what are the sources of heat generation. So we will now try to like classify the different approaches to like estimate the cell temperature. So there are so many different models that you can notice over here. So like heat generation model or heat transfer model, temperature estimation models. So there are so many different approaches, among which like the most notable ones are electrochemical models, and also what is called as equivalent circuit models and lumped parameter model. Okay, so like most commonly used ones for very quick and simple low power in terms of computation, these are the models that are used, especially these two. For electrochemical models are a little bit more complex. They're more challenging to have in terms of computation, and they don't really serve anything in terms of day-to-day EV applications as such, because this is not applicable in real life. except that it gives you a very complete and clear picture of how the cells will behave in a micro, in a molecular way or in an atomic way. So that way you can actually like use this model, but you will not be able to like use this in a realistic application. Yeah. So these are the like highlights of some of the most commonly used models. Yeah. So there are other ones as well. There is something called a single node to two node. This is basically based on the set of states you can derive per system. So that too will like once again lead to some other different levels of complication, right? So for our session today, we will limit our usage, or you can say our scope, to combination of what is called as equivalent circuit models and lump parameter model. Okay, so a lump parameter model is what we are considering. So this is nothing but a combination of electrical equivalent model and heat generation model. Okay, so heat generation is once again based on like what is the total heat being generated inside the cell, and also the electrical equivalent model. So that is what is also called as equivalent electrical circuit model. So we will explore both of these, and we will try to understand how we can go for temperature estimation using this. Right. So just to keep in mind that lump parameter model is the combination of equivalent circuit model and heat generation model. So we will now we will try to understand how both of them are. Okay, so you can see this over here. So these are the two diagrams. You can just have a quick look on this and how like both of them are used in tandem, or both of them are used together to get a like a estimate in the terms of temperature. Okay. So what is electrical equivalent circuit model? Electrical equivalent circuit model is basically the representation of the internal chemistry in terms of electrical elements. So basically you can represent all of that as an electrical circuit. Then heat generation model is basically representation of interior thermodynamics as electrical material or electrical elements. So that too is also an electrical representation. For example, you can use like resistors, capacitors, etc. In series or parallel combination to get a complete circuit. Okay, so the cycle is like this, or we can say the entire model flow is like this. We have first and foremost the electrical model, or you can say the lithium ion equivalent circuit model. So for this, we need certain data. So this data is obtained through cell testing. So there are different tests that have to be performed in order to obtain this data. Then those data is what is called as internal resistance. So that is given as ohmic resistance, polarization resistance, capacitance. So these are all basically some of the parameters that you have to derive from cell testing. Okay. So based on this, the output of the model is terminal voltage. So it will simulate a certain terminal voltage. So terminal voltage, once it is taken as an output, it is then fed into the heat generation model, right? So that heat generation model is given below over here, which is like highlighted here in the circle. So in that, if you feed in two values, that is the open circuit voltage and the terminal voltage, you get the total heat loss, which is given by Q. And once you feed that into the thermal model, you get a sort of estimate on the temperature. Okay, so this is how the model flow works. So you have the cell testing data, which you feed into the electrical circuit model. The electrical circuit model provides a terminal voltage as an output. That is used as the input to the heat generation model, which gives you heat loss. Heat loss is used as the input to the thermal model, which gives you an estimate of temperature, which is once again used as an input to the equivalent circuit model. So this is how the entire model runs. This is basically used as a feedback. So you can see the same thing being represented here. It's basically a feedback. Okay, so in the nutshell, this is basically how the entire model is developed. Okay, so now we will like see just a quick overview on what is a electrical equivalent circuit model. So it's also abbreviated as ECM. So here basically you have basically, as I said before, it is a electrical representation of the internal electrochemical or electrochemistry of the cell, and they can be represented as combination of resistors and capacitors, as you can see here. So here you can see a combination of like some resistor in series to some other resistor and capacitors in parallel. Okay, so again, here we will not go into the derivation part, because this is based on Thevenin's theorem, and this is actually very like tedious, and kind of like it'll take a lot of time to derive that, which is once again not a part of this webinar, right? So here we see like the entire resistance of the cell categorized in two parts. So one is represented by R0, that is called ohmic resistance, and R1 is which is called as polarization resistance, right? So as we had seen earlier, so ohmic resistance is because of the material, and polarization resistance is because of the internal chemistry, the chemical reactions, right? So this in this way you can actually create an electrical equivalent circuit, and some examples are there. So the one is called as RINT, so also called as internal resistance model, where the entire battery or the entire cell is just modeled as a single resistor. So there is no like definition of capacitors in series or parallel as such. It is just taken as a resistor in terms of series with the voltage source. So that is the simplest model. There are also other models like 1 RC model, 2 RC model, and then you can go on like increasing the complexity of the model by increasing the number of RC over here. So 3 RC, 4 RC, things like that. Okay, so here you can see actually in the picture on the left hand side, this is actually 1 RC. Okay, so the construction of this and how the data is brought about, all that will not be discussed here. Okay, so yeah, so this is the like simplest understanding of what is an electrical equivalent circuit model. Okay, so the output of this is your simulated terminal voltage. So next, we will like now jump into the temperature estimation using the lump parameter. So we have seen the first part of it, that is the electrical equivalent circuit model. Now we'll try to understand the heat generation model. So before we go into the heat generation model, we will try to see like what are all the analogous terms from thermal term to electrical term. So how each and every term is modeled equivalently on this side. So you can see temperature, that is the thermal property, is modeled as voltage. Heat source is modeled as current. Thermal resistance is modeled as your electrical resistance, and thermal capacity is modeled as electrical capacitance. So this is just a analogy table. So this is like only for you to understand what is the analogy used from thermal to electrical. Okay. So based on this table, we build what is called as a lump parameter model. Okay. So there are actually different types of lump parameter model. So one is there are like one state model, or you can say there's like another one is called as two-state model. There is also what is called as 5-state, and so on. So there are like many different approaches. In today's webinar, we'll be exploring what is called as two-state lump parameter model. Okay. So the single state is basically where only one temperature of the cell is considered, which is called as the bulk temperature. So it is basically a combination of the overall cell temperature, and there is no like classification as different types of temperatures over here. So that is single state, or you can say one state lump parameter model. There is an advancement to that. It is called as two-state lump parameter model. Okay, so two-state lump parameter actually is a little bit more advantageous because, as explained earlier, the single state only models one temperature. So this one models two types of temperatures. So it is actually classified into two categories. One is surface temperature, the temperature that is distributed over here at the surface of the shell or of the casing, and one is the core temperature, that is the temperature at the center of the cell. So the core temperature is basically the temperature that is like attained because of the internal reactions, and the surface temperature is because of the heat transfer from the inside to the outside. Okay, so this is basically a two-state model. Single state model usually actually combines these two and puts it just as a single value of temperature. Okay, so this is the difference between one state and two state. Then prior to going into the complete model part, let's try to understand some model assumptions. So the model assumptions is that here in this case, there is no temperature gradient or heat generation gradient that is considered. So it is just a uniform distribution of heat, a uniform distribution of temperature throughout the cell. So basically, the core of the cell as well. So it's not considered in terms of gradient. Okay. So next, even at the surface, it is considered to be uniform. Okay. So this is like basically it's a simplification. So this is just a simplification, or you can say it is a linearization to reduce the complexity of the model. So this is actually going to consider uniformity in terms of temperature. Okay. So here you can actually see in the bottom diagram here how is the two-state lump parameter model considered. So TC is the core temperature, and then followed by an electrical resistor that represents conductivity resistance. Okay, so this is called as heat conductivity resistance. So also you can say that this is a thermal resistor, right? So that is the amount of resistance that heat transfer will face every time it is transferring from the core to the surface, right? From the inside to the outside. Then TS is the surface temperature. Then RU is the resistor, the thermal resistor that is offering resistance to the heat transfer from the surface to the ambient. Okay, so this white dot here, this is the ambient. So the connection from the surface to the ambient. Okay, so both of them are considered here, and that is why this is called as a two-state lump parameter model, right? So how exactly are we going to model this, or how exactly we're going to consider this? So here you can see a set of equations. So these are the modeling equations that we use in order to obtain the total temperature gradient, or you can say the total temperature difference between T surface and T core. So it is given by a set of like first order differential equation, which is basically, it's very simple. So basically you have to consider here is your total heat input, and this part is your heat output. Okay, so this is how you are able to obtain your core temperature. So if you integrate this equation, before that you have to simplify it. So Q plus delta T by RC whole into 1 by C. So if you integrate this equation, then you will get uh, your total available core temperature at any given time, right? So if you can see all of the relative parameters, or you can say the description of all of the entire equation on the right hand side. So what all each parameter means. So Cc is your heat capacity of the core. So basically heat capacity is like how much energy it takes to raise the temperature of the core by 1 unit in terms of temperature, or you can say in terms of 1 degree Celsius or 1 unit Kelvin. Q is your irreversible heat generation. So in this case, irreversible heat generation is being considered, right? So that's your I squared R losses. Then RC, so as explained before, RC is a heat conduction or thermal resistance from the core to the surface of the cell. So TC and TS are your estimated surface temperature and core temperature values. Okay. So once you obtain this, you will use this as an input to this surface temperature. Okay. So because surface temperature is once again is dependent on how you estimate your core temperature. Okay. So once again here you can see that this is a partial differential equation. So here you have heat input, total heat input, heat in, and this side is your heat out. Okay, so heat in is always considered as equal to heat out. So once again, if you simplify this equation and integrate it, you're obtaining the total surface temperature. Okay, so and the respective description for that equation has been provided on the right hand side. Yeah, so CAC is your heat capacity of the surface. So again, how much energy it takes to raise the temperature of the surface of the cell by 1 unit temperature, so either in terms of Kelvin or in terms of degrees. And T ambient is given here. T ambient is the ambient temperature at that particular time, and RU is a convection resistance. So how much resistance is there in terms of convective heat transfer? Yeah. So this is the complete set of equations. This is how you consider what is called as heat generation model. This is the heat generation model. Okay. So this is these are the set of equations that we use. So how will we go for it in terms of modeling? So equivalent circuit model is actually pretty straightforward. We just have to know which element will come where exactly as per the circuit that we are considering. So in this, as explained earlier, we have to consider the internal resistance, which is like ohmic and polarization, along with the capacitance, which is obtained through cell testing data. And from this, we obtain the output. That output is what is called as terminal voltage. Okay, so that set of inputs and outputs you can see listed over here. Okay, so if you have these as your inputs and if you get your terminal voltage as your output, so you use the terminal voltage and OCV as an input to the heat generation model. Okay, so your heat generation model, as explained earlier, it is first dependent upon what is the difference between terminal voltage and OCV. Okay, so if you say, so the first equation that we saw, so Q is equal to how is it modeled? It is modeled as the total change in voltage, OCV minus terminal voltage into current. So total current that has been passed. Okay, so that is your heat loss. So if you take this heat loss as a input, then you're able to calculate the total core temperature. Yeah. So this is how it is in terms of modeling. This is how it is done. So this is a electrical equivalent circuit model and the heat generation model in combination. Okay. So here you can see the temperature estimation model here along with the heat generation. So as I explained, Q is equal to OCV minus terminal voltage into current I. Okay, so the rest of the part, that is the core temperature estimation and surface temperature estimation, these are basically like equations that are directly modeled in this. Okay, so the same equations that we saw in the previous slide, that is basically being used here to estimate your core temperature and surface temperature. And then once again, the surface temperature is being used as a feedback. Okay, so this way you're able to like model the whole heat generation. And here on the right side, you can see the complete set of inputs and outputs that is being used. Okay, so this is like the complete breakdown of the model of the complete temperature estimation and heat generation model, right? So yeah, once we have the surface temperature that is estimated for the cell, then we can go for simulation. Okay, so here you can just see some sample simulation results, how the temperature rises for different cases. For example, if you are discharging in the simulation at 1C versus how it will be represented in terms of 2C. So how you can see the difference in terms of temperature, right? So the maximum core temperature here is 301 Kelvin, right? While here it is close to like 310 Kelvin, right? So this is like almost like 30, 36 or 37 degrees Celsius. And here on this side is roughly around 23, yeah, around 25 or 26 degrees Celsius. Okay. So there is a noticeable difference you can see here between the core and the surface temperature, obviously, because core is always hotter than the surface. Okay. So this is a simulation result that the same model as you see previously that has been simulated. And once you simulate this model, these are the results you can expect from the thermal model. Okay. So of course, there is another simulation that you can perform. It's called as pulse discharge. So in pulse discharge simulation, basically you are providing the current as pulses, as a series of pulses. And you can see here the effect of that in terms of temperature. Yeah. So more realistic scenario would be if you go for what is called as drive cycle simulation. So where the true effect of temperature rise or temperature drop can be observed over there. Okay. So That way you can perform like different steps or different ways in which you can validate the model, and you can compare it with how it performs in realistic applications. Okay, so that is the perspective in terms of these results and how you can interpret them, right? So a quick summary. So we have seen that a two-state lump parameter is a very simple approach. It basically considers two cell temperature states, that is the core temperature and surface temperature, and you can model them very easily using the two differential equations. And you can just use them in a combination with electrical equivalent circuit model to get a pretty a decent accuracy in terms of simulation results. Okay, so although it is pretty simple, although it is decently good in terms of accuracy, it does not consider the temperature gradient. So if you observe the temperature distribution in a lithium-ion cell, you will notice that whichever format it is, if it's cylindrical or if it is prismatic or whatever, you will notice that the bottom portion is usually a little bit cooler, that is towards the negative tab, and you will notice that the upper part of the cell is usually much more hotter. So you will see that so this part actually may attain something like 39 or 40 degrees, while the lower portion actually stays something like 35 or something like 33. So usually the bottom portion is cooler, right? So as in when you head towards the positive terminal, that is the upper part of the cell, you will notice that it starts to get more and more hotter, right? So this particular model does not simulate that. So you don't know the true effect of the temperature gradient on the behavior of the cell. So it does not consider radiation heat transfer, right? So of course, cells give out a lot of heat in terms of radiation heat transfer mechanism, and this can actually affect it, in a much more broader way, especially when you're considering it in a battery pack behavior, right? So if you don't consider that, then this model is not really that accurate. So this model is not really preferred if you're going for battery pack level simulations, right? So also another thing is that if you want to go for full thermal behavior understanding, then this model is very insufficient, because it simply does not consider all the ways in which the temperature can affect the cell behavior, right? So that can be understood directly by considering the modeling method itself, because it is considered in radial direction. So right. So we had seen that the model was simplified as two parts, right? So we had seen that it was from the core to surface, and then surface to ambient. So that's all it considered. So that is in radial direction, but it does not. But of course, we know that the heat transfer is done in all directions, right? It has to be considered in the axial direction, in the vertical, horizontal directions. It has to be considered in all of the 6 different axes, right? So that way, this model actually is very highly simplified, and it does not really account for a good amount of heat transfer, or you can say more accurate heat transfer, right? So in order to counter all of this, you can go for another approach. It is called as finite element analysis, FEM, or you can also go for what is called as multinodal analysis. Multinodal, or you can also consider what is called as 5-state model. So 5-state model, or whether it's finite element analysis or multimodal, or even if you consider what is called as electrochemical model, right? So electrochemical, all these are higher order, higher fidelity, more complex models, which can actually negate all these drawbacks, and they can consider heat transfer in all the directions, model the heat transfer mechanism in a much more accurate way. All that can be done. But the drawback here is that these are extremely time consuming, and they require a very huge amount of data input, right? So because most of these are data driven. Okay. So since they're so heavily reliant on data, the amount of time and amount of complexity that is involved in this is simply too much, that this itself becomes a big challenge in order to implement. And plus, moreover, these models cannot usually be used in terms of algorithm development, especially when you're considering BMS application, right? So that way you have to establish a good trade-off between in terms of model complexity and model simulation simplicity, right? So that is why in most cases, people either go for single state or two state lump parameter estimation, because this can be directly used as a combination with electrical equivalent circuit model, and many of the simulation parameters simply like becomes much more simplified, right? So that way, like this is a short summary or a short conclusion that we can derive from the two-state lump parameter model. So of course, there are many improvements that can be made by considering five-state or many other such models. But once again, you have to consider the application scenario. Yeah. So that is the end of today's webinar. I will be providing all of the references. So there are few references that you can use. So the many majority of the two-state or majority of the five-state model has actually been described here, and you can go for understanding in depth based on these research. Yeah.